Right, so this is the fourth examples class, and today we're going to be having a bit of a look at convergent sequences using this notion of absorption that I introduced, and having a bit of practice at working with definitions again. So this is sort of reinforcing how to work with definitions to prove some results which are, some of them very quick, almost too quick, as you'll see, and others which need a bit more thought. So the idea is to work on questions 1 to 3. I don't think we'll finish those. If some of you, however, get through questions 1 to 3 really quickly, there are questions 4 and 5 available. So in lectures, I introduced this non-standard notion of absorption, saying that a set absorbs a sequence if, from some term onwards, every term of the sequence is stuck inside the set. So some people say the sequence is eventually stuck inside the set, or the terms of the sequence are eventually in the set, or only finally many terms of the sequence are outside the set, that sort of thing. But the nice thing about making the set the subject of the sentence is you can say the set absorbs the sequence, and that will help a bit later, as we'll see. And sometimes you're interested to know when does the set absorb the sequence. And we'll say it absorbs it by stage n, capital N, if all the terms from that term onwards are inside the set. So you can specify that it absorbs it by a particular stage. If it absorbs it by a particular stage, it'll absorb it by a later stage too. And some other standard things we had in lectures. If a small set absorbs the sequence, then a bigger set has to absorb it as well. So if A is contained in B and A absorbs the sequence, then B has to absorb the sequence too. So that's absorption. And then there's what does it mean to say that a sequence converges? And here is the definition, the official definition for the notes. It's on your question sheet as well. And you're going to need these definitions in a moment because you're going to be essentially asked to substitute in a definition in order to solve the first question. So here is the epsilon n definition of convergence in R to the D. The sequence xn converges to the point A. That means that for all epsilon greater than 0, there is a capital N that's a natural number, so that all the terms from then onwards lie in the open ball centered on A, radius epsilon. That is the standard definition of convergence of a sequence in R to the D. So you're supposed to use those two definitions that you've got there, and you're going to be substituting them in a moment. Now, question 1 has got 2 parts, one of which is very slightly harder than the other one. Actually, quite a bit harder, I think. The first part is to show, for a given point A in R to the D in a sequence xn, that these statements A and B are equivalent. A is that the sequence xn converges to A. B is that for every epsilon greater than 0, the open ball B epsilon of A absorbs the sequence xn. You can say that another way, that every open ball centered on A absorbs the sequence. And that's one reason I like this use of the word absorption. Now, part 2 is a bit harder, where you're asked to show that B is also equivalent to another condition, C. Well, all three of these things are equivalent. The third one is that every closed ball centered on A absorbs the sequence. Now, that is not going to be exactly the same as your standard definition of convergence. So that's going to need a bit more thought. I suggest you start on part 1, and we'll come back to part 2 in a bit. So if you finish part 1 very quickly, you can start thinking about part 2, but I'll give you some more hints in a bit. So your task in part 1 is simply to substitute in the definition of B epsilon of A absorbs the sequence and read off the fact that it's come out to say exactly the same thing as the definition of sequence convergence. That's all you have to do. So if you substitute in correctly the definition above for B epsilon of A absorbs the sequence, you should find that it says exactly the sequence converges to A using the other definition you have above. So just look on your question sheet, substitute in the definitions, and see how quickly you can do that. I'll pause the recording there, and we'll come around and see how you're getting on. So you've had to think about this. The idea is simply to substitute in the definition of absorption and what it means to say that B epsilon of A absorbs the sequence xn. So first of all, I'll remind you what that means. So note, by definition, B epsilon of A absorbs the sequence xn means that there exists some natural number n such that every term from then onwards is in the set being B epsilon of A. That's the definition of absorption. Now, if you substitute that in to B, B says that's true for all epsilon greater than naught. All epsilon greater than naught, that happens. So all I did was I substituted in the definition of absorption into B, and this is what you get. But that's the definition of convergence, which we had earlier on the sheet. So that's precisely the definition of convergence, or convergence of this sequence. So it's precisely the definition of xn converges to A. So you've done a proof by definition substitution. By the time you've substituted in the definitions, both the statements say the same thing. This is the easy bit. That shows that A can only be simply because they say the same thing by the time you've substituted the definitions in. Okay, but part 2 is a bit harder. Part 2, what are you faced with? You've got the definition of absorption and B that says that every open ball centered on A should absorb the sequence. But C says that every closed ball centered on A should absorb the sequence. Now, it's not true that if a closed ball absorbs a sequence, in general, that the same radius open ball has to, because the closed ball's got more points in than the open ball. If an open ball absorbs a sequence, then the corresponding closed ball will as well, because it's got more points in, so it will still absorb the same sequence. But if the closed ball absorbs a sequence, you don't know that the same open ball does. However, B and C have got extra information. They both tell you that it's true for every positive radius. So every positive radius open ball centered on A absorbs the sequence is one of them. The other one is every positive radius closed ball absorbs the sequence. That's the other one. And those are the things you've got to show are equivalent. So what happens is that B implies C is trivial, but C implies B isn't. B implies C is trivial, but C implies B needs some thought. So what are we going to be allowed to use? So here are the hints. Remember, if A is a subset of B and A absorbs the sequence, then B absorbs the sequence as well. That's helpful. And the second observation that may help you is that the epsilon that appears in condition C is a dummy variable. You could use any other letter. C is equivalent to another condition, C prime, which says that for all epsilon greater, sorry, not epsilon this time, let's say for all delta greater than naught, it doesn't matter what letter you use, the closed ball radius delta centered on A absorbs the sequence. So I suggest you take those two hints and you have a go at part 2, see if you can prove that B implies C and that C implies B, possibly using C prime to help you. So I'll pause the recording there. So you've now had a go at that, and I think you've seen some of the issues that come up. I think that many of you are now happy with B implies C, and have seen that C implies B needs a bit more work. So let me just point out why these things are true then. So we've got B implies C. Since the open ball is always contained in the closed ball, if the open ball absorbs the sequence, then so does the closed ball. And B implies C is immediate from that. But the converse needs a bit of thought. So for C implies B, we're given that every closed ball centered on A with positive radius, we don't allow radius 0 for our balls, absorbs xn. And we have to prove B. B says something happens for all epsilon greater than naught, so we have to start then with the all-important let epsilon greater than naught. And now we have one of these optional diagrams. We're trying to prove that the open ball centered on A and radius epsilon absorbs the sequence. Now we know the closed ball radius epsilon centered on A absorbs the sequence, but that doesn't help us because there might be some terms in the sequence on the boundary of this set. So we need to use a smaller closed ball. So what we do, let me just make that a bit rounder. So what we'll do is we'll look at a smaller ball. Let's take radius epsilon over 2 and make it a closed ball. And that's the end of the optional diagram. By C prime, if you like, with delta equals epsilon over 2, the closed ball radius epsilon over 2 centers on A absorbs the sequence. Remember, C prime was just rewriting C using a delta. But since this closed ball is contained in the original open ball, the open ball absorbs the sequence as well. Which is exactly what we needed to prove. And we finished. Any questions about that proof? Yes? Back up a little bit. How much further up? The optional diagram or a bit further? Bit further? Bit further. So you know that every closed ball with positive radius absorbs the sequence. You're trying to prove that every open ball with positive radius does as well. You do a let epsilon greater than 0, and you prove that the open ball radius epsilon absorbs the sequence, using the fact that the smaller closed balls do. Any more questions about that proof? Yes? Sorry? Yes. No. The open balls are the subset of the closed ball with the same radius, but a closed ball with a smaller radius will be a subset of the open ball with a bigger radius. So the question there was, which open balls are contained in which closed balls, and which closed balls are contained in which open balls? Now, if you take the same radius and set it on the same point, then the open ball is contained in the closed ball, and the closed ball isn't contained in the open ball. But assume they've got the same center, and one of the radii is strictly greater than the other, then it's the radius that counts. So it's only if they've got the same radius that there's an issue, once they've got the same center. If they've got the same radius, then it's the open ball contained in the closed ball. But if they've got the same center and different radii, then the one with the bigger radius contains the one with the smaller radius. Okay, any more questions on that proof? Further down, okay? I suggest that some of you might start thinking about question 2. Question 2, you're given a specific sequence which you can prove by methods from last year that it's a sequence that tends to 0. And the idea here, given it tends to 0, that means that every little open interval centered on 0 should absorb that sequence. That means you should be able to figure out how far you need to go to get close to the origin. And this question gives you a very crude way of doing that. How far do you have to go to be absolutely sure that you're within a millionth of 0? Now, it's not a particularly good estimate, and you could do much better, but it will do for our purposes. So moving on to question 2. We've got this particular sequence, n over 2 to the n, and we're supposed to use the binomial theorem to show that 2 to the n is strictly greater than, this is just n choose 2 here. So that's a binomial coefficient n choose 2, which is, that's why you'll use the binomial theorem to prove this. And once you've done that, then you can see about how far do you have to go to be absolutely sure you're stuck inside this interval. I'll give you just a little bit of time to think about how you can make that estimate, and then I'll give you my version. So I'll give you just a few minutes to have a go at this, and then I'll run through the solution. Okay, so you've had a bit of a look at that. Let me give you my version of this. So, first of all, let's look at part 1. And I'm using the fact that 2 to the n is equal to 1 plus 1 raised to the power n. And so if we use the binomial expansion for that, so for n greater or equal to 2, and the reason you need to be greater or equal to 2 is you need to get a term with a 2 on the bottom to come in. For n greater or equal to 2, 2 to the n is equal to sum from, I'll put it in the form 1 plus 1 to the power n. And by the binomial theorem, that's the sum from k equals 1 to 0 to n of n choose k, 1 to the k times 1 to the n minus k. Those ones are obviously irrelevant. That's equal to sum from k equals 0 to n of n choose k. And note that k equals 2 does turn up, since we've assumed n is greater or equal to 2. And all the terms are strictly positive, so that's greater than n choose 2, which is what we wanted. So that's the binomial coefficient n choose 2. So that proves 1. For part 2, the question is, how far do you have to go along the sequence n over 2 to the n before you're sure that you're close to the origin? So you've got xn equals n over 2 to the n. So by 1, we've got 0, of course, is less than xn, is strictly less than n over n minus 1 over 2, which is equal to 2 over n minus 1. And that's a very crude estimate. It's much, much smaller than that when n is big. But this is good enough for us, because we can already use that to guarantee that if n is at least 2,000,001, you're going to be within a millionth of the origin. Let's have a look at that. So how big should n be to guarantee that 2 over n minus 1 is smaller or equal to 10 to the minus 6, because we've already got a strict inequality in there. So if we can get that less than 10 to the minus 6, we'll be home. Well, 2 over n minus 1 is less than or equal to 10 to the minus 6, if and only if multiplying up 2 times 10 to the 6 is less than or equal to n minus 1, which is if and only if n is greater or equal to 2,000,001. Now, as I say, it's a very crude estimate. It gets into there much earlier than that, but you can be absolutely sure that if you take n equals 2,000,001, or n equals anything bigger will do, like 3 times 10 to the 6 will do, then that open interval, minus 10 to the minus 6, 10 to the minus 6, does absorb the sequence by stage n. As I say, actually it absorbs it much earlier than that. As an extra exercise, you might want to figure out when does it absorb it by? Can you do some better estimates than that? But this will do for this question. Any questions about those estimates? Okay, then we'll stop the recording there and give you a break before the lecture.